Okay, so there's a million ways to skin a cat. So when you're talking about finding out what your rivers are in your watershed, there's a couple ways to do that as well. So let's create a new model, and we are going to feed it the flow accumulation as an input, and we're going to go to our hydrology, and we're going to do I apologize, we are not going to go there. We're going to go into map algebra, and we're going to do a raster calculator. So we can just drag that in, and we're going to open it up, and we're going to say flow accumulation is greater than 2,500 meters, and we'll output our raster as ACC 2500.tiff. Go ahead and apply that, hit OK, and let's run that. Okay, so the model is finished and the output is here. So anything that does not meet is put in 0. So basically we have extracted all of our rivers in our data set, and we can now use these as input to stream feature. Okay, so now that we have our stream data, we can go ahead and convert the stream to a feature, and we're going to feed our TIFF as input stream raster. And we're also going to feed it our flow direction. Okay, so I'm going to go ahead and change the output into our watershed database, and I'm going to call it rivers 2500. Save, apply, and let's run it. Okay, so now that our model has finished, we'll get rid of some of this, and we can see how to do this as an iterator. And so we'll keep a for iterator, and we'll go ahead and set our values. So from 2000, and we want to go up to 5000, and we want to do it at a 500 meter interval, or 500 off flow interval. So now this value can be input as our snap distance. Okay, so we are going to need a few things. We are going to need an input, which is going to be our... Okay, so for this model, we are going to be doing a snapped pour point. So we'll go ahead and put this in. And for this example, we are going to be simulating a outbreak or a spill contamination. So we're going to add another city here, and let's just say that our suspecting cities let's say that our suspecting cities are Yergalum and Leque. We'll verify and apply, and we'll go ahead and feed this into our snapped pour point. And we're also going to feed it our flow accumulation. Go ahead and name it. Okay, so in order to use our for iterator, we're going to use a snap, and that's the name of our raster layer, and then we're going to put % on either side of n, and that means that it's going to put an automatic number after the name snap. Go ahead and hit OK and apply, and we can feed this for iterator in as our distance. Okay, so now we also want our watershed, and we want our snap feature to feed our watershed as our pour point data, and we're going to add in our flow direction and also feed that into our watershed as our flow direction. Go ahead and rename your file. When I'm naming the file, I'm also going to use %n% as automatic naming. Click apply, and let's run the model. Okay, so now our iterations are done, and it's created 6 snaps and 6 watersheds. Okay, so now let's look at what our watersheds look like, and these should change based on the snap distance. So you can see as we go farther out, it looks farther out and includes more watershed for its snap distance. So this will show you what your effect of changing your snap distance can be on a watershed to find an intersecting monitoring point for both of these points here. So now if we want to explore our rivers on top of there, then we can just add them in, or we can, an easier way to maybe do that is just to drag our layer to the top, and now we can see all of our rivers in here. And if we zoom in, we can see that to monitor both of these possible contaminating cities, we actually would have to monitor a much larger area because this is theoretically the 5,000 snap point that we would have to use in order to monitor it, which would tell us that we could set a monitoring here and it would work fine. Now let's compare some existing data just to see how close everything lines up. So this was a mapped river network. And you can see that actually ours is maybe even better than this data set. It is more, has more linking because of how the DEM is a 30-meter spatial resolution DEM, so it is pretty coarse resolution, but you can see that this data set here, maybe this is caused by migration of the river, but our data set may or may not have had better resolution than this, and you can especially see it in the curves that our DEM picked up. Okay, so in order to do some calculations for this area, let's go ahead and make a new model. For the input, we are going to feed it our watershed, and we are also going to do a comparison, so we're also going to feed it another watershed. So let's do a conversion tools from raster to polygon, and let's find out what the difference between our area of our first watershed and the area of our last watershed is, so then we can compare them. Okay, so I've gone ahead and named the outputs, and let's and save them in my personal geodatabase. So let's go ahead and run it. Okay, so now we have two areas that we can input and do a comparison to tell the difference between area 1 and area 2, where both of them are going to be monitored on this stream here. There are a couple ways to do this. First, you could just do a raster calculation, or you could do a calculation in the tables here. So that's what I'm going to do. Okay, so one way to put these together is just to simply start editing. Click on the one that you want to copy, and then we'll paste it into our 5000 layer. Now we have two features in our 5000. We can save our edits and stop editing. Okay, so I've done a quick calculation by dividing by 1 million. So that is taking 1000 meters times 1000, which is a million, and finding out how many square kilometers each area is. So now we can see that there are about 200 square kilometers difference from the first to the second.